Hi, everyone. I'm sorry that I can't be there with you today. Unfortunately, I came down with a gnarly case of food poisoning last night, and so I am at home, but I wanted to make sure that we could get through the things that we would have gotten through in class today because you still do have your assessment on Friday, especially because today's class was primarily talking about 2.15, excuse me, and then spending the remaining class time studying. The class yesterday had about 20 minutes at the end. So what I'm going to do is I'm going to actually go over a lot of the questions that they asked me because I imagine that there's probably some similarities. So for your classes today, you will have your assessment on Friday, the 23rd. As a reminder, your Unit 2 progress check is due by the start of that class because it's supposed to help you study. And then I do have extra help tomorrow during DEX and tomorrow after school from 3:30 to 4. Also, please be mindful, Mr. Mulig is available for you to answer any questions, and he's aware that I'm not there, so that way he can help prioritize your questions. So for today, we're going to talk about topic 2.14, multiple choice. We'll get into the Brian Passwater 2.15 notes and practice. We'll discuss the Unit 5 assessment, and then with whatever remaining class time you guys have, you can go ahead and study for your assessment. So here we go. Oops, I have it on the annotating. Okay, so with question number one from last night's homework, we know that the Richter scale, right, is an exponential function with a base of 10. However, intensity is measured in that it increases multiplicatively by a factor of 10, and the Richter scale increases additively by 1. So therefore, with intensities, we're thinking about logarithms. So essentially, all you have to do to actually solve for this function is make a base of 10, and you're doing 10 raised to the 5.1 minus 2.5. And so at that point, like we are just saying, we're just figuring out how much more intense the actual earthquake was going to be. So even though you have a calculator for this one, you could still do this without a calculator just by setting it up. So again, you can see this right here and understanding that the Richter scale is going to be our exponential function with a base of 10. With multiple choice number two, you're given 2 points on a logarithmic function, and then we know that they're on the graph. We want to know which of these equations could actually be true. So what we want to do is we want to go ahead and take 2 and we want to plug it in for x. And if we get an output of 1, that's a good sign. So if I do log base 4 of 2, well, 4 raised to the x equals 2, the only way to do that would be x equals 1/2, and that's not the case here. So we know that A can't be the option. We go to B then. So we have 2 times log base 2 of x. Now, log base 2 of 2, we know that log base 2 of 2 is equal to 1 because 2 raised to the x equals 2. The only option is a positive 1. However, we are taking this 2 and then multiplying it by 1, and therefore our output would be 2 comma 2, which is not true, and therefore does not work. So we move to C. We plug in 2. So log base 4 of 2, as we said before, is going to equal 1/2, and then 2 times 1/2 equals 1. So that's a really good sign. We just have to check the other coordinate to make sure it's true. So log base 4 of 4 is going to give you 1. 2 times 1 is 2, and that's our other coordinate. So that's what's nice again about multiple choice is you can just plug in values sometimes and see which one is true instead of having to create this whole graph and go from there. For FRQ number 3, right? Obviously, this is a calculator question, but you can still think about how to set this up. So we're given the life expectancy, which is modeled by the function L, and we know it's a logarithmic function because of the ln. We know L of x gives the life expectancy in years for x decades after the year 1900. So what we want to do is we want to plug in 80 for L of x because based on the model, we want to know when is the first time, aka the input, that the human life expectancy is expected to be 80 years. So at this point, you have 80 equals all of this, and you have a couple options for how to solve. You could go ahead and you could just graph 80, y equals 80, and you could graph y equals all of this and find where the point intersects, and that would give you your answer. The other option is you could solve logarithmically. So if I have 80 equals all of this, I'm going to subtract the 42, divide by the 13.86, and then I'm doing base E raised to all of that math equals X. That one's going to be a little bit quicker. And again, you don't have a calculator for your assessment, but you still can do the algebra, which is the important part. A quick note about this though. When you do solve, you're going to get x equals 14.931. Now, as a reminder, this said it's x decades after the year 1900. So we're going to take that 14.9, we're going to multiply it by 10, and then we're adding that to the original 1900, which is why we end up with the late 2040s and not late 1914. That one's there to trick you because you got the answer, and so you just make an assumption in that case. For multiple choice question number 4, you are told that in a certain town, the population in the year 2000 is 30,000. The population grows at a rate of 2.3% per year, and the time is measured in the years since 2000. Which of the following functions gives output values in years since 2000 for input values of the town's population? So essentially, all we're doing here is setting up an exponential function, and then we're finding the inverse to make it a logarithmic function. And this is one of the most important things to take away from Unit 4 and 5 that I know some people struggled with last year is understanding that exponential and logarithmic functions are inverses of each other. So if you're not sure how to set up the log equation, set it up as an exponential and then just swap x and y and solve for y in that case, and you have your inverse function. So actually, A is the exponential setup in this case. So now from here, if we wanted to go ahead and rewrite this, right, we would think about the fact that, okay, in this situation here, right, we want to get all this by itself. So moving it over, right, we swap the f of p and the p. So p would equal all of this. We divide by 30,000, which is how we end up with p divided by 30,000. And then from there, we have p divided by 30,000 equals 1.023 raised to the f of p. From there, we know the base is 1.023 of p divided by 30,000, and that would be our final answer, right? So again, set up the equation, find the inverse. That's it, which is actually really nice when you realize this because it's a non-calculator question, which, you guys know how to do this math. I know that for sure. And then the last one that we're going to talk about is number 5. The initial population size of an animal species is measured to be 2,000. The population doubles every 8 years. So we want to be careful with that setup because we're either going to do 8 times x or x divided by 8 or 1/8 x. So I want you to be careful and think about that one. So which of the following functions gives the time in years as an output value and a certain number x for the population size as an input value? So once again, set up an exponential function, find the inverse to make it a logarithmic. So in this case, right, I think it's on the next slide, it is. We have y equals 2,000 times 2 because it's doubling, raised to the x minus 8. As a reminder, if this was 8x, that means that it would happen 8 times in a year, right? And that's what we have to be careful of. It says it doubles every 8 years, not 8 times in a year. So for most of us, that's probably where we may have gone astray. So from here, right, we're swapping the x and the y. We're dividing both sides by 2,000, which is how we get our x divided by 2,000. And then from there, right, we're going to go ahead and change it to log base 2. And then at that point, we are just solving with our value, which is fantastic. And then lastly, this one I said lastly before, but this one is going to be, it will not be on your test because again, you're given a whole set of data. You're asked to find the regression equation. That's important for a plus b ln of x. And that would mean that we're going to go ahead and do data and statistics, or we're going to do lists and spreadsheets, data and statistics, and then we're going to find the logarithmic equation. So obviously that you can't do on your assessment, so just be mindful of that. Okay. So with our Brian Passwater 2.15 notes in practice, I will give you these notes next class, but you can just go ahead and follow along on your own if you would like. So with these, we're going to be talking about semi-log plots. So essentially what's going to happen is a semi-log plot is where our y-axis is changed to be scaled logarithmically, and the x-axis still is going to stay additive. So as a reminder, an exponential function has an additive input and a multiplicative output. When we take when we do a semi-log plot, we're basically taking the outputs of the exponential function and we're just logging them. So for example, I want to show you what I mean by that. If we go over here to our Desmos, okay, and you look at this over here, we have an exponential function, as you can see by the green dots. 2, 4, 6, 8, 10, 12. We are increasing by 2. And then 3, 9, 27, 81, right? This is this is multiplicative by a factor of 3. So if we want to take the semi-log plot, all we literally do is we leave the inputs the same, and now we're just actually just taking the logs of the outputs. And when we do that, let's go ahead and shut this one off, and we'll turn this one on, and we're going to zoom so you can see. Notice what happens. It becomes a linear function. So by taking the log of the exponential outputs, we are able to linearize our function. Again, the input values did not change. The output values just became a log. And then just be mindful, please. This is a log with a base of 10, which is why when you look at your notes, you're going to notice that we have a base of 10. So let's go over here quickly so you can see that. Okay, so for example, number 3, in this situation, you are given 4 different graphs and you're asked to determine which one has a vertical axis that's logarithmically scaled. Well, again, we just talked about the fact that a logarithmically scaled axis means that we have a base of 10. So the inputs are staying the same, the inputs are staying additive, and they are going to be over equal length input intervals, whereas the output values are going to be 10 raised to the 1, 10 squared, 10 cubed. So that's how we end up with D as our option here. But if we were to think about plotting this, when we look at 1 comma 40, right, it's 1 and then 40 is right here because this is 10, 20, 30, 40. That line represents 40, which is why when we're at 2, it's 2 comma 60, right? When we move up to 135 and 203, we go above the 100. This represents 100 and oh, sorry. That actually represents 200, my bad, because in order to get from 100 to 1,000, we're going to go with the 200 right there. Okay, so that's basically how we're thinking about plotting these. And if I were to go ahead and move forward a little bit more, if you were to think about where all these get plotted, it's the same rule. So 0 being the x-axis, 0 to 100, right? We're going to go 0, this is 100, and then 200 would be right here. If we're doing 1 comma 25, it's 1, this is 10, this is 20, this is 25. If we're doing 3.2 comma 800, we're going to approximately right here, and then 800 is going to be all the way up here. So 200, 300, 400, 500, 600, 700, 800. So if I go ahead and click forward to that answer key, you can actually see where all of those values exist. So plotting points on a logarithmic scale, again, we just have to be mindful of the literal scale that we see on the y-axis. So from 1 to 10, 10 to 100, 100 to 1,000. Okay, so now if we are to backtrack quickly, the semi-log plot, as I mentioned, comes from taking the output of an exponential function and making it the input of a logarithmic function. So that's how we end up with a graph that looks like a linear function. So how do we convert exponential to linear? Well, we have an exponential function right here. We actually just take the log of the initial value and the log of the base. And when you are to type all this out, this gives you a constant, that gives you a constant. So it's basically y equals mx plus b, which again is going to be our linear function. So log base a represents your y-intercept and log base b represents your slope. Okay? And then again, please just be mindful, as we talked about, again, we're taking the x and that's staying the same, and then we're taking the log of the output of the exponential function, and that is how it's going to become linearized. So let's go ahead and move forward with this. We went through those. Yeah. Okay, last thing. All right, so the last thing with our semi-log plots, and as a reminder, topic 2.15 is not on your assessment. 10 to the 1 is 100, 10 squared is, sorry, 10 to the 1 is 10, 10 squared is 100, and 10 cubed is 1,000. So again, we saw this before. These are these coordinates plotted. Now, if we wanted to write the equation for the linear model for the semi-log plot, we can go ahead and use our first 2 coordinates. So in order to find the quote-unquote slope, which is log base n of b, we are doing the change in y over the change in x. So we're doing the log of 60 minus the log of 40 divided by 2 minus 1. That gives us our rate of change, which is going to give us that slope value. From there, all we need to do is just plug in a value for x and a value for y, and now we're able to solve, right, for our other constant value. So if I'm to click ahead over here, right, we can see all of that. Again, we're using the log of these. this was the original exponential function, but since we linearized the data and made it a semi-log plot, we are doing the log of the output values. Okay, so that was your crash course on topic 2.15. That's honestly exactly what we would have done today as well. This will show up as one multiple choice question on your AP exam. And so we'll do a learning snapshot with this next week. We'll discuss it a little bit more, obviously. I'll give you the handout unless you want to print it on your own. And then we will move forward from there. So let's go ahead and chat about your Unit 5 assessment. So as a reminder, your Unit 5 assessment is on topics 2.7 to 2.14. Again, 2.15, not on the assessment. That will appear as a learning snapshot later, and then it will pop up on your mock exam and your AP exam as a singular multiple choice question. For your assessment, 10 multiple choice, no calculator, 2 FRQ, no calculator. Again, for FRQ number 1, we're doing function concepts, and for FRQ number 2, it's going to look like FRQ number 4 on your AP exam with symbolic manipulations. So actually, let's go ahead and look at that quickly so you remember where you can find these in case you forgot because we had a long weekend, right? But hopefully all of you are sitting there going, oh my God, it's on the topics page. And thank you all again for your patience. I wish I was there with you, obviously, as opposed to this. Okay, so on the topics page, if you scroll down on the left side, right, we have our review materials, and then I made a whole section for you about the FRQ practice. So if you click here for FRQ number 1, we're going to go ahead and see that we have a data table and an equation. You could end up with a graph and an equation, a data table and an equation. So you'll end up with 2 out of those 3 things. So from here, again, you're finding the composition of functions. So you're looking for h of 1. We'll discuss what's important here with restating the statement. You're then looking for the values of x when f of x equals 4. So going over here and thinking about it from that perspective. And then we're thinking about, okay, if we plug in an output, how do we solve for an input? Now, again, you would have a calculator on your AP exam for this question. Since we do not have a calculator for our assessment, you're just solving using logarithms, which we've been doing this entire unit. So you can solve without a calculator with these logarithms. Think, for example, log base 2 of 2, we know equals 1, or log base 4 of 2 is equal to 1/2, and being able to solve. You will also have to determine the end behavior as the function increases or decreases without bound. So you're going to want to go back and study what the logarithmic function looks like as a graph and how our transformations impact that, whether it's flipping over axes, getting stretched, whatever. And then lastly, you're going to determine if the data table is linear, quadratic, exponential, or logarithmic, and then you're justifying it based on the inputs and outputs. Now, I do want to reference something for you with that. So an important note on your AP exam for FRQ number 1, when it says you're writing a sentence to justify the function type based on inputs and outputs, you must use the values in the table for your reasoning. So see how it says refer to the values in order to earn full credit. So basically, f of x is a logarithmic function because the input values increase or decrease multiplicatively by a factor of 4, and the output values increase or decrease additively by 2. So you're just stating the literal value with which they are increasing or decreasing. Be mindful, again, outputs are additive for logs and inputs are multiplicative. And then one more note for FRQ number 1. When you're responding to an FRQ, you are solving for something. So you must rewrite the answer. So think of it like your English class. So if you're solving for h of 5, you must write for your final answer, h of 5 equals, and then give your final answer. You can't just put a final answer, and it's really crucial for this particular question because if you look at this example 1, we have an f of x, we have a g of x, and an h of x. That's 3 different functions. So you have to make it abundantly clear to the AP reader that you understand which function you are solving for. Or if you're solving for x, you're saying x equals in order to earn that full credit. So please be mindful of that. Okay, this is the last thing I want to go over with you guys today. And actually, I want to point out where this lives on the topics page. If you scroll up slightly, I added a lot more practice for topic 2.13 because again, that really is the crux of this unit. So if you look at worksheet D here, worksheet D has lots of practice with solving without a calculator with base E. So I highly recommend doing this particular worksheet. So if you look at this worksheet right here, In order to earn full credit, you have to simplify all the way. So if you get down to something like log base 3 of 3 or ln of e, you have to rewrite that as a 1 because we know what that value equals. You cannot leave it in its log form. So if we were to go ahead and do this question right here, we know m of x equals all of this, and we know m of x equals e in order to solve for x. So we're going to replace the m of x with the e. Unfortunately, my trackpad's not working, so I'm just going to walk you through. So again, we're replacing m of x with e. From here, we're adding 5e to both sides. We get 6e. We're now dividing by 3 because we're trying to isolate this e to the 4x. We end up with e to the 4x equals 2e, right? And then from there, we now are going to convert it to a logarithmic function because we're stuck, right? We can't access this x unless we invert it. So we're basically saying log base e of 2e equals 4x. So again, log base e of 2e equals 4x. And as a reminder, we rewrite log base e as ln. Now from here, and this is where some of us, this is why I really want you practicing this. You might just end up giving a final answer that says ln of 2 divided by 4, which is not entirely wrong. It's just not entirely right. So you have to simplify it all the way. So in order to do that, we see we have 2 times e. Well, we know if we multiply those expressions, that means that we can expand them by adding. So essentially, this becomes ln of 2 plus ln of e. And again, we know ln of e is equal to 1, so we replace it. So from there, we have 4x equals ln of 2 plus 1, and we divide by 4. And that would be our final answer. So with the remaining time in class today, I want you guys to go ahead and choose your own adventure. As you are studying for this assessment, you can do all the activities on the topics page. You have your progress check. I did just want to make a quick note. You're not going to see change of base on this assessment. So do not stress about that, especially since I'm not there right now. I am going to just give you that little nugget that you will not see change of base. So just be mindful of that. All right. Well, I hope you guys are doing well. I will see you tomorrow, either during DEX or after school for extra help. And or you do have Mr. Mulig in the math lab today as well. All right. I will talk to you guys later. Have a great day.